2.1 Basics of Functions and Their Graphs, Day 1. So in this lesson, we're going to find the domains and range of a relation. We're going to determine whether a relation is a function, determine whether an equation represents a function, and evaluate a function. So first we start off with the definition of a relation. It says a relation is any set of ordered pairs. All right, any set, no rules. If it's a group of ordered pairs, it's a relation. All right, so remember, though, an ordered pair has an x and a y. And so it says a set of all the first components of the ordered pairs is called the domain. So when you list all of the x values there, that is your domain of the relation. And then the set of all the second components is called the range of the relation. So when you list out all your y's, you get your range. All right, so for example 1, it says find the domain and range of this relation. So for our domain, we're going to list out all of those x values. So our domain is a set of numbers that includes, we have 0, 10, 20, 30, and 40. For our range, remember the range is a set of the y's. So our range is going to have the set of numbers that include the 9.1, 6.7, the 10.7, 13.2, and the 21.2. And so that is our domain and range. Now, the definition of a function, it says a function is a correspondence from a first set called the domain to the second set called the range, such that each element in the domain corresponds to exactly one element in the range. So, what you've learned in the past is that for it to be a function, x cannot be repeated. So if we're looking at a group of ordered pairs, like we did in the previous example there, none of our x's can be repeated. So look at example 2. So determine whether this relation is a function. So look at your x values. Are any of those repeated? If your answer is yes, then it's not a function. If your answer is no, it is a function. So we look at this one. We have a 1, 3, 6, and 8. None of those are repeated. So this is a function. If I'd included the ordered pair 6, 7 with it, then because a 6 would have been repeated, that would have caused it to not be a function, okay? Now, if an equation is solved for y and more than one value of y can be obtained for a given x, then the equation does not define y as a function of x. And so normally when we look at equations, we try to solve for y, and we can do that here. But the thing is we're looking for where y is going to have more than one solution. So where we're going to have like y is equal to something that's positive and negative. And so what will cause that is if we're looking at like a y squared. So if I had like x plus y squared equals 2, and I subtract the x, then I'd get y squared would equal the 2 minus x, and we'd have to take the square root. But remember, when you take a square root, you end up getting plus or minus whatever your answer is over there, okay? So because you got that plus or minus, that means that this is not a function. Now the other thing that we talked about that gave us a plus or minus was also an absolute value. So if I had like x plus the absolute value of y equals a number, then again I could just get the absolute value part by itself, just like what we did before. And then remember, what's inside can be positive or negative. So what's inside could be positive equals the other side, and what's inside could be negative. And so in that case, when I solve them, I end up with two different answers. Therefore, this is also not a function. So the two things you're really going to watch out for, okay? So what's going to make it not a function? If you have y raised to an even exponent. It can be an odd exponent, okay? Odd exponent is no big deal. But an even exponent, when we take that even root, we have to put plus or minus, therefore not a function. Or we have to look out for that absolute value of y. Okay? It can be absolute value of x, that's no problem. That's a function. But absolute value of y is going to give us a not a function. So watch out for those two things. So knowing that, look at example 3. Does this equation define y as a function of x? Well, I look at that y value. It's not in absolute value bars, but it does have an exponent that is even. Therefore, this is not a function. If that had been an odd exponent, it would be a function. All right, and then we have our special notation that looks like this. We've all seen it. Whoops, sorry, marked it out on accident. So it's read as f of x or f at x, and it represents the value of the function at the number x. So our example says if f of x is equal to x squared minus 2x plus 7, evaluate f of negative 5. So I'm going to write this right underneath here on purpose. All right, so if I have f of negative 5, look at these two. What is the only difference between them? Where we had an x, we now have that negative 5. Remember, what you do to one side of the equation, you're going to do to the other. So everywhere there's an x, we're going to put a negative 5. And so I'm going to start with building what I call a skeleton. So a skeleton is everywhere there's an x, I'm going to put parentheses in its place. So I have x squared minus 2, there's an x, I'm going to put parentheses, and then plus 7. And then whatever we replace the x with on the left side, we have to replace the x's with on the right side. And then we're just going to simplify that. Now, something I should have mentioned on the other page, okay, this is function notation, that f of negative 5. Notation, no touch, okay? You're not trying to get f by itself or anything like that. We're not going to even work anything on that left side. That is just our notation. So when I go to work this right side here, I have negative 5 squared. Well, remember, squared means times itself, so negative times a negative is a positive. 5 times 5 is 25. Then we have negative 2 times negative 5, which is positive 10, plus 7. 25 plus 10 is 35, plus 7 gives us the 42. So we know that f of negative 5 is equal to 42. Now, I know that's the last example that's on your notes, but I want to go ahead and look at one other thing, okay? What if we had, instead of evaluate f of negative 5, it said f of x plus 2? So it's the same idea. So now we have f of x plus 2. So again, everywhere there's an x, I'm now going to put x plus 2. So I'm going to go to the other side here, and I'm going to open a skeleton. I'm going to make it a little bit bigger this time because I have more to write in that blank. So notice there's my x squared, parentheses, minus 2. There's my x with the parentheses, and then I have my plus 7 still. Now, so inside there this time, though, whatever we plugged in on the left, we plug in on the right. So we're going to put x plus 2 in here. Now remember, when you have a binomial squared, you can't just distribute the x. The exponent. It doesn't work, okay? You're going to have to remember that squared means times itself. And so if we write it out, that we know then that means we're going to have to go to our box. Now I'm going to go ahead in the same step. I'm going to distribute the negative 2. So minus 2x minus 4, and I'm going to bring down my plus 7. So now I'm going to come over here on the side, and I'm going to draw my box. And it's x plus 2, x plus 2. Remember, we're going to multiply. And then we combine our like terms and write our answer. So from our box, I got x squared plus 4x plus 4. I'm going to bring down my minus 2x minus 4 plus 7. Now, if there had been a number in front of the x squared at the beginning, I would need to distribute it. In this case, there was no number written, so it's like a 1, so I'm just going to distribute my 1. So I get x squared plus 4x plus 4 minus 2x minus 4 plus 7. And then all we have left is we need to combine our like terms. And we're going to write our answers in descending order of the exponents. So we have an x squared. And then we have, 4x minus 2x, which is 2x. And then we have 4 minus 4, which is 0, plus 7, which is a positive 7. So we found that f of x plus 2 is equal to x squared plus 2x plus 7.